All right, so today we're going to be looking at limits algebraically. There are two ways to look at limits algebraically. First, just put the number in, and evaluate is a really good way of doing it. If you can plug the number in, like here on number 1, if you can plug in 4 times 2 minus 3 and work it out, then that means you can do it algebraically. But the second method is simplifying and then putting it in algebraically, and that goes back to our rational functions. What we did on the last unit. So if you can't plug the number in and go 8 minus 3 is 5, then it probably means you need to do some kind of math to work out the problem more. So in this next question, we've got the square root of negative 3 plus 4 equals the square root of 1, which is 1. So we just plug it in, do the math. So stop the video and do these 3, and come back here in just a few minutes and check your answers. So in checking your answers here, we're looking for the tangent of 0 plus pi over 4, which is just pi over 4. Pi over 4, if you remember, is the point, the square root of 2 over 2, the square root of 2 over 2. Tangent is y over x, which is the square root of 2 over the square root of 2, which is 1. And number 4, 1 squared plus 1 to the third power is going to be 2 to the third power, which is 8. And in number 5, negative 2 minus 1 plus 3. Negative 3 plus 3 does not exist, because you can't take the square root of negative 3. That's imaginary. So if I had chose to put 2 in here, that would have worked, wouldn't it? I could do 2 minus 1. That comes out positive, but I can't do negative 2 minus 1. So if it doesn't come out to be something you can calculate, most of the time it has a reason why. This one happens to be radicals can't have negatives inside. All right, let's look at the second method then, because the first method seems really easy, right? You just plug a number in. Everybody agree with that? Well, I can't plug 2 in the bottom of this problem, because 2 squared minus 2 times 2 is 0. So when you have rational functions, restrictions cause a lot of problems. 2 happens to be a restriction in this problem. And so as long as I'm giving you restrictions, you should be doing the same thing we just did in the last lessons. And that means reduce it and see what you can do with canceling. Limits, but I'll send you a video so you can watch it and send you an assignment, because I mean it's something totally different. All right. Well, I didn't pause the video. Oh well. All right, so when you're looking at these, you want to factor them, just like we did in the last lesson. Whatever factoring it takes. If you can remove it, it causes a hole. If you can't remove it, it causes a vertical asymptote, right? If you have a vertical asymptote, you would have to graph it, because you'd want to know, is it going up on both sides or down on both sides? Which makes the algebraic method not totally algebraic, right? But if it's a hole, I can calculate it algebraically, because it's the same thing as finding the y value of the hole, which is why I spent time in the last unit teaching you how to find the y value of the hole, because I can use that for this lesson. So in this part, x minus 2 cancels out. Doesn't that get rid of y I can't plug into? Yeah, it gets rid of that x minus 2 part. So now my function is the limit of x as it approaches 2 of x plus 2 over x. And I can plug 2 in that, because 2 plus 2 over 2 is 2. Because 2 plus 2 is 4, and divided by 2 is 2. Too many 2's in that problem. Mm-hmm. So If it's a whole, you can evaluate it. If it's a vertical asymptote, you'll have to go back and look at the graph or do a table. That would be your only two choices. So now, in this question, what times what makes negative 12 add up to negative 1? Okay, negative 4 and 3. And we know the bottom's x minus 3x plus 3 because that's food line, difference of squares. So in this problem, the negative 3 is the issue because of this x plus 3, right? So that's the part that's canceling. So I've got rid of the part that's causing the problem. I got rid of where the hole is. Right? What's causing the hole in the problem is x plus 3. And x plus 3 is what's causing me not to be able to plug this in. So now I can redo my limit and say the limit of x as it approaches negative 3 of x minus 4 over x minus 3, I can plug negative 3 in that. Negative 3 minus 4 over negative 3 minus 3 is negative 7 over negative 6, which is 7 over 6. So that process that we spent a lot of time on, learning how to do the math for finding the hole, is what gives us an opportunity to do the math on these questions. Now, let's say in this last question, instead of asking for negative 3, I'd ask for positive 3. Positive 3 is a definite problem. Everybody agree? See, I couldn't plug positive 3 in this problem after canceling because it still makes the denominator 0. And that's where you would have to go to the graph and look at it and say, well, is it going different directions and doesn't exist, or are they going the same direction, all positive or all negative direction? And those vertical asymptotes, you can't tell that algebraically, other than you can see why you can't plug it in. All right. Now we have all kinds of functions in this lesson. In our last unit, there was a little bit more focus on quadratics. In this unit, they're going to throw more cubics in there to make sure that you know how to do all kinds of functions. And so we have both cubic patterns here in terms of we have a binomial one that uses a special pattern with SOAP. We have 4-term cubics. And we even have a 4-term quartic down here that we're supposed to be able to do all the fine tuning of factoring by hand to get all these answers. So, I'm assuming that I can't plug one in even into this one, because otherwise why would they give me this fractional problem? So I'm just going to start off by factoring because obviously that's what they're wanting me to do. What is the cubic method for 2 terms? What do you do first? Cube root. All right. What will that make? X minus 1. So now we see what's going to happen is that's going to cancel out and I'm going to be able to plug 1 in. But if I can't get that parentheses right, I'm not going to get the answer right. How do you get the second parentheses? Square the first. Square the last. Do what? Nope. Close. Just times. 1 times x. I'm assuming 1 times x over here is x. Now, it's same as the original problem. Opposite of the original problem. Always positive. This is the one that doesn't double the middle, because if you double the middle, it's factorable. And that second parentheses in a cubic is never factorable. So now I can cancel out that part of the problem that's causing the hole so that I can rewrite my question with the simplified polynomial and plug it in. 1 plus 1 plus 1 is 3. 1 squared is 1. Plus 1 plus 1. So it makes the math go a whole lot faster when you simplify it. Now, sometimes with a question like this one, you may find you want to separate the question out a lot because you've got to split the problem on top and split the problem on bottom. You may want to go over to the side and say, okay, let me split this problem. Take out an x squared. That leaves me with x minus 1. Take out a 1. That leaves me with x minus 1. That leaves me with x minus 1 is one parentheses, and x squared plus 1 is another one. Can I go further on the squared one? Yes or no? No, why? Is that a minus? It's plus, yeah. You can't do it when it's plus because it can't be different signs and be plus, y'all. So I've got the top as far as I can go. So I bring it back over here and write it down so I can see how to cancel, and we do the bottom. So I can take out a cube, and that'll leave me with x minus 1, and I can take out a 2, and that'll leave me with x minus 1. So I have x minus 1 and x cubed plus 2. Now, that kind of reminds me of the first question. Can I cube root that? I can't cube root the 2, can I? So that's the answer to that part. So once you've done your grouping and you get it all factored and you're sure that the second parentheses doesn't factor with the power in it, then I can see why 1 was such a problem. Because I got an x minus 1 on the bottom. But it's going away. So since it's going away, I now can plug my number in and say 1 squared plus 1 over 1 cubed plus 2 is 2 over 3. So the key to these questions is really just looking at specifics about factoring so that you can cancel out the part of the problem that causes the issue, because the issue's at the whole, and makes it to where you can plug the numbers in so you can evaluate where is that hole at. So it's the same thing we did to find the point for the hole. That is the value, 1 2/3 is the point of the hole. And that's what the limit helps you to find, the y value of that point. Now, if it didn't cancel out, like for example, if the top had been x plus 1, the bottom had been x minus 1, and it didn't cancel, then I'd go look at the graph to see what the vertical asymptotes are doing. But then that's more like what we did yesterday. That's not algebraic as much. All right, so algebraic's all about plugging the number in, or if you can't plug the number in, factor it. Cancel and plug the number in. So it's basically plugging the number in. Now, the second thing we want to look at today I haven't got written up yet. Hold on. Okay. Yeah. Okay, we're going to look at some one-sided limits a little bit and talk about how could I evaluate it if I only want to know what it's doing on the left side or the right side. And we'll go more in depth in this in a few minutes, but I'm just going to kind of hit a couple of highlights that relate to what we were just doing. All right, so to relate what we did yesterday to what we're doing today. Yesterday we looked at the graph of everything, and we talked about did the right and the left meet so we could find the limit of the whole question. Today we're going to focus on sometimes just the right side or the left side of the picture. So let's look at the graph of 2x plus 3. That's a y-intercept of 2, up 2 over 1, or down 2 over 1, down 2 over 1. A straight line. Does everybody agree with that? And here's the point they're talking about. First of all, do they meet there? So that means both answers would be the same, whether I'm doing the left or the right, wouldn't matter, would it? Is that because I can plug the number in? So if they ask you to do a left or a right, and you can plug the number in and do the math without doing any simplifying, guess what? You just plug it in. because it meets 5 on this side, it meets 5 on this side. The answer is going to be 5 either way because you can plug the number in. Now, what if you're looking at this one? Let's do a trig example. Doesn't hurt to go back and review a little trig. If you remember, sine of x is that problem that goes 0, 1, 0, negative 1, 0, right? Everybody agree? 0, 1, 0, negative 1, 0. There's pi over 2. Does it meet? So if it meets on both sides, that means that it doesn't matter if I look at the left or the right, they have the same answer. Why? Because I can plug in the number and work it. I know the answer of sine of pi over 2. And since I know it automatically, that means that I can just evaluate it, and I don't have to worry about they're talking about the left or they're talking about the right. Because they always meet. If you can plug the number in, it means it's colored in, and you can meet on both sides at the same number. But if they give you either rational functions or if they give you piecewise functions, it takes a little bit more math to figure out if you can get the answer to the left or the right. So let's look at a few examples of that. All right, I slightly changed the first question to make the second question so that we could look at something that was really similar but not exactly the same. So don't think these are both exactly the same. All right, everybody sees y2 can't be plugged in the bottom, right? Neither one of these questions can 2 be put in the bottom. But if I can factor and cancel that out, then I know they meet at a whole. Does that make sense? So if I can make this x minus 2x plus 2 and cancel that out, that caused a whole. And it always meets at a whole. Which means that the left and the right would have the same answer. And I just plug the 2 in and get 4. So as long as it causes that whole, it doesn't matter if I'm talking about the left or the right. Because look at the equation of x plus 2. X plus 2 would be a y-intercept of 2, go down 1 over 1, down 1 over 1. And, excuse me, down 1 over 1, up 1 over 1. Up 1 over 1. The whole would be right there. Somebody tell me why the hole's there. What did I evaluate? I plugged in a 2 and I got a what?
4.
Over 2 up 4. Whole. Right? Don't they meet on each side of that hole? It's a straight line, but there's a big gaping hole in the middle of it. So the key here is, as long as you know it causes a hole, you can do left and right the same way you do just plugging it in, except you got to simplify first. Now, that's a vertical asymptote. Somebody tell me why.
But it doesn't cancel.
Right, I can't factor the top to make it cancel. So because this is a vertical asymptote, I can't plug 2 in there and work this problem. I have to graph it. I have to figure out what is it doing on each side of that vertical asymptote. So that's where I'd want to go and use the graph. I'd go to y equals and I'd type in parentheses x squared plus 4 parentheses divided by parentheses x minus 2 parentheses zoom 6. So as you can see, there's a vertical asymptote right here, and I can barely see that piece of the graph up there. But I think we can tell this is going to negative infinity. Want to take a wild guess what the other one's doing? So therefore, when I talk about the whole entire limit, it doesn't have an answer, right? But if I just talk about the left, the answer is negative infinity. Because to the left of this line, it is going to negative infinity. Because it is going down forever. To the right of that line, it's going to positive infinity. So when I only ask you for the left or the right, you have to look at the graph to see where is it going because it's a vertical asymptote. Does that make sense? I can't plug the number in, so I got to look at a graph. That's my only other choice besides making a table. So therefore, my graph did something like this.
So we can tell for sure that's a vertical asymptote.
Because something doesn't cancel. That's a vertical asymptote. And so because it asks for the left, I just look to the left of that dotted line to see what's it doing. So the answer to this question is negative infinity. Because to the left, it's negative infinity. To the right, it's infinity. The whole answer is none, but this didn't ask for the whole answer. It asked for left. That's what a one-sided limit does for you. Everything has a one-sided limit answer unless there's no graph over there. There's always an answer for one side unless there's no graph. So that's why you have to be able to sometimes look at the graph to figure it out. Because not everything is algebraically workable. All right. So now let's look at an example. What number am I on? Okay, because I skipped a few in here that were repetitive. Let's look at one that has a radical in it. Well, what am I putting 2 2's for? It's supposed to be putting an X. All right. I want to look at an example of a radical because I want you to see the difference between sometimes what can happen with radicals. And I have 2 examples of a radical. I want to look at the difference between what if you have a radical but there's just a radical in the denominator versus what if you have a radical and there's more math than just the radical in the denominator. Now first of all, in these questions, it's not that you don't want to rationalize the denominator, but in this question I definitely don't want to rationalize the denominator because it's more than just a radical. It's an addition problem. So can I plug that 2 in? Let's see. 2 minus 2 is 0. Square root of 0 is 0. Plus 1 is 1. 1 over 1 is 1. As long as you're able to plug it in and work the radical out, and it doesn't make the denominator 0, you're good to go. But if you plug the number in and it makes the radical 0, would it help to rationalize the denominator? That's what you need to think about. So let's talk about rationalize the denominator on this one. Would that help? Because right now everybody agrees I can't plug 2 in there. That makes the denominator 0, right? Okay. To rationalize the denominator, you put the same square root on top and bottom. That's why it can't be an adding or subtracting problem. That's a totally different method, and we'll talk about that in calculus. So that makes a radical on the top and drops the radical on the bottom. Did that fix the issue on why I can't plug the 2 in? I still can't plug the 2 in, can I? Doesn't exist. Wait a minute. Am I doing a right or a left on that? No. Okay. So this one would exist whether I talk about right or left. Would everybody agree with that? If I said what's the limit of x as it approaches 2 from the left, it still would be 1 because I can plug the number in. But if I talk about the limit of x as it approaches 2 from the right or the left on this one, I don't know if it's got an answer or not because the whole problem doesn't exist. Does everybody agree with that? Well, let's look at to see if it has a right or a left. Let's look at the graph of this. So when we go to y equals and type 1 divided by the square root of x minus 2, and then I just get rid of the rest of it. Would have been easier if I'd have cleared the row first, but I didn't think about it. Zoom 6. Okay, so my graph starts right here. And I'm talking about 2. Do I have an answer to the left of 2? Why? Because there's nothing there. Okay, now, do I have an answer to the right of 2? Are you sure? Okay, I'm going to change the graph and box this in a little bit over here. Or, I'll tell you what, let's look at a table. That might be a better way of looking at it. Because we could look at some values right before 2, right? So let's do that. So if I go to the table, and I want to look at some values right before 2. What are these values right before 2 doing? Getting bigger, and that tells me it's going to where? Up forever. And what's it going up to ever mean? All right, now let's go back to the graph. Does it really look like it's going up forever? That's because this calculator has some issues. There's a vertical asymptote right there, and it's trying to draw a line straight up, and it can't draw straight up. It doesn't know how to draw vertical. So that's why you might need to look at the table to see, did it really go up forever, or did it really stop there? Because some square root graphs actually stop on a point, and it would have an answer on that point for the right. That's a number. But when the square root's in the bottom, it's usually something about going up or down forever because it causes a vertical asymptote. So the positive side on this graph would be infinity, and the negative side would not exist, which is why the whole answer doesn't exist, because it doesn't have the same answer for both of them. Now, let's look at a piecewise function and talk about it. Okay, 16. All right, so we've been asked to look at the limit at 0. And it didn't ask me for right or left. I'll put up a right or left one in a minute. Let's talk about one that don't have right or left again first. So if they ask me for the limit at 0, that means I have to know whether or not the graph has a hole at 0, it's colored in at 0, or if there's a vertical asymptote there. And in this particular question, they say the first equation works for everything but 0, and the second equation works for 0. So one thing that I'd like to know is, would they have the same answer? Because if they do, then that means that in this particular question, you could talk about the limit existing because they have the same answer. So this one's going to have a big gaping hole at 0 because it says don't use 0, right? But if I plug 0 in, I get 0. So I got a big gaping hole at 0 that's at 0 at the origin in that graph. In the second equation, I have a quadratic. It says plug in 0. But if I plug in 0, I get 0. If these two match, that means not only do they meet there, but it's colored in. Because they match. Because what it means is they graph the first one. I don't know what the graph looks like. Let me just graph it on the calculator. X cubed, was that minus 3 plus 3x, right? Ah, thank you. One of these days I'm going to remember to turn that off because I don't like math print because I stay up there in the power all the time. Alright, so if this is my function for the first one, as you can see it went through the origin, right? But that was the only value that they told you it couldn't be. Everybody agree? So there would be a hole right here if that's the only function I had. But the second function colored that hole in because it said the answer was also 0. So one function can color the other function in, or you can have pieces. So when you have one that's not equal to and one that's equal to, you want to know, what it kind of looks like for the not equal to one because it colors everything in but that one. And then if it colors this one in or not, doesn't make any difference, really, because they do meet, even if it's not colored in. Would you agree? So whether they're colored in or not, the answer to this question would have been 0 either way, because in this graph, they meet on each side of 0, whether this one colors it in or not. But this one also colored it in helps to make the answer come out to be 0. Now, let's look at that question in a little different way. What if I factored the first one? And what if I factored the second one? Can you see why 0 is a problem? Right. So sometimes with these questions, when you start looking at them, you can look at them in a variety of different ways, but I can see why, with the factorization, that 0 is a big issue in both of these equations, because I took out an x, and x would be equal to 0. Now, this is a fractional problem, so it's not a restriction, but I can see why that would be an issue. All right. Let's look at one more piecewise. What number am I on? 17? Okay. All right, so the limit of x at the purchase. I'll come back and fill that part in a minute. Okay. There might be one in the book, and I could actually just copy one out of the book so I don't have to make one up off the top of my head, because that will take longer, because I want one more. Okay. X to the third minus 1 over x squared minus 1, 2. 3 over x plus 1. Yeah. X is less than 1. Okay, so let's talk about finding the limit of this problem at 1. Now, in that last example, the second equation filled the first equation in. Let me go back and talk about that a little bit more in depth. What that did is made the graph continuous, because there wasn't a hole in it anymore. When I colored the second equation in, it colored the hole in. That's important in calculus. You want functions to be continuous. And doing the limit of a function and proving it's continuous is an important feature. Obviously, in this problem, we want this one to stop at 1, 2. And this one to pick up there at 1, 2 and keep going for it to be continuous. If it's not, then I hope at least these two pieces meet. Because if these two pieces don't meet, then I don't have a whole either. So the key here is to a piecewise function. If you wanted to decide if this function has an answer at 1, then you've got two things you have to think about. One, do the greater than and the less than have the same answer to at least cause a hole there? Or if it has an answer that's the same, if it's even 2, like this constant here, then that would fill the hole in. So that's like two separate concepts. Do they have the same answer? And is it the same as the point in the middle? Either way, it's got a limit if they have the same answer. So one of the things you do is plug a 1 in. Can I plug a 1 in that?
Yeah.
Can I plug a 1 in that? Okay, I can plug a 1 in this one. What's that answer going to be? So that'll be 3/2. Can I plug a 1 in that? No, I need a factor. That's the one we factored earlier, so I'm just recopying it out of my brain. All right, so we factored x cubed minus 1 a few minutes ago, and it came out to be that top, and we know what food line is, and this cancels. Does that make me able now to plug in 1? I hope it comes out 3/2. Otherwise, this answer has no answer whatsoever. So 1 squared plus 1 plus 1 over 1 plus 1, is that 3/2? Okay. So this one came out 3/2 and this one came out 3/2. That caused a hole in my graph. Because 1, 2 is not 1, 3/2. Does everybody see that? There's a big gaping hole in my graph. You've got to have these two the same to have a limit. It does not have to be the same as this constant. So what you've got here basically is two pieces of a graph. And on each side of 1, you've got this piece of a graph that meets at 3/2.
So it's like constant there for no reason.
No, it's there for a reason. At 1, 2, there's a colored in dot.
Oh.
Okay? At 3 over x plus 1, there is an open circle at 1, 3/2. And then you'll have a piece of a graph over here. Maybe it's doing like this. I don't know what it looks like. I'm just going to make up some. And then over here, you might have a piece of a graph. Let's say it came down like that. I don't know. And they met here. But it wasn't the same answer as 1, 2. But at least they met because they have the same answer. So this graph is not continuous because they all three would have to have the answer 2. But at least it has a limit of 3/2 because they met. Now, that graph is not accurate. I'm just trying to illustrate it without knowing what it looks like. Well, let me rephrase that. That part might be accurate. This part over here, I have no idea what this piece looks like off the top of my head. So you want to make sure that your greater than and less than answers have the same answer. If you don't have a greater than and less than answer, then the answer to the problem is going to come from the not equal to, like this one. The not equal to actually gave the answer to this question. I could care less that this one colored it in. The limit has to be, where does it meet? And this graph meets on both sides of 0. This one just colors the dot in. That just makes it continuous. So this graph is continuous because it colored the hole in. So this graph is not continuous. This one has discontinuity. Discontinuity at x equals 1 because it's got a hole there. Discontinuity is when there's a hole in a vertical asymptote. So if you got something that's not colored in, you've got discontinuity. If you've got it colored in all the way because every piece of the formula came out the same answer, that's continuous.
So if you didn't have a constant there, like on the other one.
Mm-hmm. Mm-hmm.
Constant on this part, that's what makes it.
Well, no, this constant need to be 3/2 for it to be continuous. It's got to have that because there's a hole here. Okay? Now, if they take that out, to fix that problem with what you're asking about, if they take this out, then one of these needs an equal to mark under it, color the hole in. Because that hole has to be colored in for it to have an answer. So the equal to part has to match the greater than less than part. All right. Now, I'm almost finished with this for today. Let's see here. Make sure. Yeah, that's pretty close to being done, I think. All right, let me write up the assignment so you can write it down, and then we're going to do some college placement test review to finish up that last page and one question. So tonight, you're going to have a two-part homework assignment. First, you're going to have 13.2, which is on page 956. And you're going to basically look at, a lot of them you're just plugging a number in. About half of them you're just plugging the number in and evaluating. The other half you got to simplify it and plug the number in. And that's going to be 2 through 32 even. And then on 13.3, which is one-sided limits, which is on page 963. It starts off with a graph that they're asking you to pull the answers off the graph. So that won't take you very much time, but I'm going to skip a few of the questions at the beginning because it's not limit work, and do just 8 through 32 even. And about, I don't know, 6 or 7 of those are looking at a picture they've drawn and just pulling the answer off. And some of that's just like the previous page, but it says left and right, one-sided limits. All right, does everybody understand what the assignment is? All right.